Hi, I'm Darren Corn, and this is my submission for my Lab 3 Digital Design Fundamentals, the Brainless CPU. So, despite this being a lab where we create a brainless CPU, we don't start with that, obviously, because we need to create the components to actually build the digital CPU. So, the first component we were tasked with making is the 4-bit register, and here that is in the flash. Essentially, what this does is it stores a single bit value, or sorry, a 4-bit value, using four data flip-flops, and this is done using an input and then an enable feature, and it's synchronized with the clock, so it's synchronous. So every rising edge of the clock will update Q if a reset is not enabled. So the reset will override no matter what and clear out any value we have in Q. So just to demonstrate this, we have enable on, uh, turn any value to, and notice how we have a 2 here, but it is not updated yet. The moment this clock, however, turns to 1, we then update to 2. And then even when it's off, it remains a value. Now, no matter what, whenever this reset is clicked, even if enable is on or anything, this value of 2 will automatically be reset to 0. And that is a very um, surface level examination of this. For more in-depth trial, I will take you now to my GTK wave. All right, so here we have the test for the 4-bit register. Um, and simply I test all the functionalities. So in the first clock tick, I'm just simply resetting everything using that reset function. In the second clock tick, I'm setting all values to 0 and showing that nothing is outputted. If nothing's inputted, nothing's enabled, just nothing. This is 0 state. Um, and then in the third clock tick, I set my input to 1, and because enable is off and reset is off, uh, even though even though I have an input, there is no output because enable is not on, even when the clock tick happens. And then I set my reset value and enable value to 1 to see what happened, and once again, nothing happens because even though enable is on, we are resetting when the clock hits the rising edge, we are still resetting, so the reset takes precedence and it's still set to 0. Now here we have a positive state where enable is on, reset is off, and when the clock is at 0, nothing happens. But the moment that clock ticks up to 1, we get an output of 1 that corresponds to the input. So the input equals the output here. And just to prove that, uh, or just and then in the next signal I show overriding and changing, updating the signal. So notice how in the first half of the clock signal, in that lower half, I change the input to F, but the output does not change. Enable stays at 1, but the output does not change until the rising edge of the clock happens, and then the input that we gave it outputs on to the output onto the key value. So notice that there's a lag between every input and output if we input before the clock signal. Um, and then the last test simply shows that if we then switch to a different stimulus, a different input, and then just reset it, doesn't matter what the different input is, uh, we will just get a value of 0, even before the rising edge. The F drops the moment we hit that reset. So the F doesn't maintain until the clock signal, so the reset doesn't rely on the clock signal, only the updating the input and output does. Um, so yeah, so sorry, updating the output does, but the reset just overrides that and switches it immediately to 0. So that's what that demonstrates here, and that is the functionality of my 4-bit register. All right, so my next circuit that we were designing with making in order to create this um, ALU circuit was just a demonstration of, or not ALU, sorry, this Brainless CPU was a basic counter. So this incrementer is attached to a always active 5 volts, making this always high. And essentially, we enable this. Nothing happens to the output. However, at every clock speed or every clock tick, sorry, this Q value will increment by 1 using that 4-bit register that we just made. And so it increments the value of our input every time, and then when we have enable on, it enables that 4-bit register to then store the value. So as you can see, every clock tick, we tick up, and that just continues incrementing up until F, which it will then go back down to 0. So here we have that incrementer, and again, that reset value will override and just automatically, no matter what is on, will change that value to 0 indefinitely. And that is my programmed counter. The next and more applicable uh, circuit design that we were tasked with creating was the program RAM, which essentially creates a way to store a 16-bit, sorry, not 16-bit, a 4-bit data value into 4-bit addresses. So essentially, you can write 256 bits or stores 256 bits of data because 16 times 16 is 256. So just to show you how this functions, we essentially have two inputs, an address and a data in. So, and then also a write and a clock once again. So, this program RAM actually has, here we can see the address values and the values assigned to them. So it has a separate text file where I can externally assign a value to each address beforehand. And here we have in this text file, in the address 0, we have assigned 3, and in the address 1, we've assigned 5. So because address 0, which is what we're currently selecting, is assigned to a 3, even though we haven't written anything or done anything, it already contains the 3 element. And we can see that because if we add, or if we make a select for the first address, which we can see should route to a 5, it does indeed route to a 5 here. So that just is a way we can preset our RAM. However, if we want to update our RAM or just update inputs into each addresses, update our addresses, what we can do, so if I want to fill out one of these addresses, say like I want address 2 to contain a 10, right, in A. So in A, what we do is we data in A, right? And then we do write that into the RAM. And as you can see, nothing's here, but that's because the clock, this clock is not automatically controlled, so we have to turn on the clock. And then when we click turn on the clock, then we get an A. And as you can see, when we go back to our address and value table, we can see that address 2 is now routed to that A value, and that is forever. So now if we unwrite it and then change this to whatever value, anytime we go to address 2, it will always be that A unless we write and then clock it to something else. Unless we write it to a different number, which we can do. And we can also edit pre-existing addresses. So say I don't want address, say I don't want address 1 to be, or address 0, sorry, to be 3, which it currently is 3, right? Say we don't want it to be 3, we want it to be 5. We want it to match address 1. We would simply change address to 0, so we're selecting for address 0, change data into 5, because that's what we want our value to be, write that, and then have a high clock, or turn the clock to 1, which we do. And now that or not permanently, but that updates address 0 to 5. So then we have 5A, and if we go into here, and we go all the way up to 2, we have A, we have 5, and we have 5, which is exactly what we programmed. And so theoretically, you could program any of these, and you can make them hold any amount of bits of data that you, or up to 15, obviously up to F. So you can hold 16 in each cell, and there are 16 cells, so you can hold 256 bits of data theoretically in this one single bit of RAM. All right, so now that we have all these components, we can finally create the brainless CPU, which is seen here. So I know it's a lot, and I'm not going to explain all of it because I'll go into some more depth with the testing, as you will see later. But essentially, this is a microprocessor that doesn't have a brain, so it doesn't do any of the logic. So all this is manual. All these inputs are manual. And so this is a couple of functions, and the main three you can see here are the three outputs. So we have an ALU. It's created with an ALU, a 4-bit register, two 4-bit muxes, one that deals with the accumulator, and one that deals with the input, the data input, and then we use the RAM to store values. Um, and so you have these three outputs. One is the output of our ALU that we created in the last lab. The other is the value that we are storing, the accumulator. It accumulates over time, so it adds up and can only be changed by adding to it or resetting it. And the data bus, which holds the value that is in either the address that we are reading or the data that we are inputting. And so, like I said, I'm not going to go into any real testing on here. Um, I will leave that all for the GTK waves, but here is that brainless CPU. So here is the external write test that I conducted. So essentially what this test was testing for was that we can externally write the value of an address in the RAM using the data in function of our brainless CPU. So as you can see in the first clock cycle, we just reset all the components to 0. In the second clock cycle, I'm checking for the address, I'm reading the address value of 2, or the address bus 2, with it, and it has a value 0 in the data bus. So as you can see that the value of address bus 2 is 0 originally. And then in the third clock timing, I am setting data in equal to 3 and writing the data in value to the address bus 2. Uh, and then in the fourth time diagram, I am verifying that the value of data 3, which I now turn off to 0, is still has been saved and stored in address bus 2, which is true because when data in is 0 and we're checking the address bus 2, we are reading address bus 2. The value of the data bus is 3, so the output's 3. So now we successfully saved the value of data in to the value of data out in address 2. So here we have the timing diagram for the internal write to the brainless logic circuit. And essentially what this is trying to do is write the accumulator to an address onto the ROM. Or the RAM, sorry. So I used four clock signals in order to accomplish this task. The first one is just resetting everything back to 0. The second timing is essentially reading the RAM value in the first, or sorry, technically the 0 address. So essentially, as you can see here, we read the value of the uh, 0 address because our address is set to 0, and I have that set to 3, the default that we have. And on the rising edge of the clock, and we're passing this value through the ALU and loading it into the accumulator, as you can see here. And on the rising edge of the clock, in that 10 to 20 nanosecond region, is when the accumulator receives the value of 3 and essentially stores it. Uh, and now in the second timing diagram from 20 to 30 nanoseconds is when we turn on the accumulator to data bus here, and we also are writing it. So we're writing the accumulator value of 3 into the address bus of 1 here, as you can see. Um, and that then uh, will change the current RAM value of 5 in address bus 1 to the value of 3 that we set on the accumulator. And as you can see, this output is true because when we reset everything once again by turning reset on, and then we address bus remains on, or remains set to 1, and we then, instead of writing, we read what is on address bus 1, we get a 3 in data bus, meaning that we successfully were able to map the accumulator value of 3 into the data bus uh, in the address of 1 internally, uh, changing the value of bus 1 from 5 to 3. All right, so the final test that we were doing was testing the ALU's two other functionalities. So the two functionalities that I decided to test were the AND functionality and the subtraction functionality. For the AND functionality, I first off reset the values, and then in the next clock cycle, I used the address value of 0 to get the value of 3 by reading it here. So notice how I keep reading constant throughout my entire thing. That's because I'm simply taking the already assigned values in my RAM instead of using data in to put my own values in. So in address 0, we currently have 3 stored in there. So the data bus reflects that value, and because I'm passing it through the ALU has that value. And then once the clock cycle happens, so does the accumulator hold that value. And then in the next clock cycle, I change the address to 1. I'm still reading this, so and my address value of 1 is set to 5 in my array. So we get a value of 5 reflected in the data bus. And because I'm no longer passing this, it's essentially the value of 5 has gone into the B input of my ALU, and the value of 3, oh sorry, the value of 3 has gone into the B input of my ALU, and the value of 5, the new value of 5, has gone into my A input. And when you AND 3 and 5, 0011 and 0101, they both share the bit of 1 in common in the ones place, and therefore in the ALU we output a value of 1, and then when the clock cycle ticks, we get a value of 1 in the accumulator, so it is now stored there forever until we reset the accumulator or edit it in any other way. So that is the AND functionality, showing that we can take two different numbers, binary numbers, and AND them together using our ALU. The next functionality that I tested was the subtraction, and I started off in a very similar way, in the exact same way of assigning the ALU with a value of 3, uh, and the storing the accumulator value of 3 using the address 0. But then this time in the second clock signal, I do something a bit different, and I activate my inversion in my arithmetic, essentially performing two's complement. I'm inverting it, doing the ones complement, and then adding 1, doing the arithmetic, um, and then adding the two numbers together. So in this case, because I have 5 and 3, like I said, my 5 becomes my A value, and my 3 becomes my B value in my ALU. That's what the ALU considers. So when this ALU does the arithmetic or the ones complement, um, it inverts my 5. It inverts my A value. And so my 5 becomes, I believe, a 10. Yeah, it becomes a 10, and then add 1 to it, so it becomes an 11, or a B value. And then so what it actually does is B plus 3, which gives us E. And if you do the conversion back using two's complement, we get E is converted into -2 using the significant bit and making that negative. And that's exactly what we get here. So let me take you back to the GTK wave. So we have we have that address 1 being selected with arithmetic and invert. So it inverts the data bus value of 5 into E, because it's adding the inversion of 5, which is 11, plus 3, which we get 14, which is E in hex. And then once the clock signal ticks, we get an E uh, sorted to the accumulator. And the 9 changes because it does another addition problem, because we still have the arithmetic on and the inversion on. But ignore that because we were able to store the arithmetic. So the 9 does not matter. We don't need the ALU output because once again, the task was to assign the value of the ALU to the accumulator, which we successfully did. So yeah, there is my tests. All right, and yeah, and that's the lab. Thank you very much for watching, and have a great rest of your night.